Okay, so let me kick us off here. So now this starts the official PDH session number 1. So, okay, let's get started with our first session of the day. I'm excited to welcome Mike Singer, Associate Principal at Northrich, to discuss Air Handling Units 101. If you're watching this live, remember to download your PDH certificate at the bottom of the webpage after the presentation. And for those watching on YouTube at a later date or listening on the podcast later, please check the video or podcast description as to how to get your certificate, because a lot of people will watch these later and email us for certificates if that's allowed in their state. Mike has extensive experience in air handling systems and will share foundational knowledge in real-world applications for engineers and technicians alike. Let's dive in. Mike, what is happening?
Hey, Tony. Honored to be here today, and I'm looking forward to talking about air handling unit basics. So this is a talk that my team and I have put together over the years. And whether you're a new, right out of school engineer in the HVAC space, or you're weathered and have some experience, you'll get something out of this today. I'm going to talk about system types.
I like the term weathered.
Yes.
I feel quite weathered.
As opposed to old. Sounds a little better. So we'll talk about system types, constant volume systems versus variable air volume systems. I'll move pretty fast through that to get to the more fun parts of this conversation, which in my opinion are the box. What is an air handling unit? Well, it's a box that has a lot of components inside of it, but how do we go about sizing that box out? We'll talk about what's inside the box with a very large highlight on economizers. So if you're looking for something a little bit more in depth, that's when you're going to want to pay attention. And I'll move on to at least introduce some of the other components we see inside of air handling units. We won't get too deep into the rest of them. We'll give a general, hey, this is what you can have inside and this is how it works. And then at the end, I'll introduce some questions to the audience and hopefully take some Q&A. So again, I'll move pretty fast through the constant volume and variable volume, but let's go ahead and get started. You ready, Tony?
Excellent. Yeah, this is a good topic. I think, my extensive knowledge tells me that air handlers are an important part of the HVAC system, if I'm not mistaken.
I would say so. One of the most expensive as well. So you want to get them right.
Yeah, for sure.
Okay. So we've got constant air volume systems, CAV, and we have variable air volume systems. Let's first take a look at some of the generalities of constant air volume systems. In today's world, they're going to be less common, way less common, due to the adoption of VAV systems over the past few decades. They're going to provide single zone control capability. So I have one air handling unit that's constant volume. I have one thermostat, one zone. We'll get more into that as we roll forward. So typically we're going to find these in older buildings where we haven't seen upgrades into a VAV type of system. They're less expensive. We don't have a VFD on the fan motors. We don't have all of the sensors we would be required to have in a VAV system, and we don't have VAV boxes. So it's going to be a simple install and a pretty inexpensive first cost. And they actually work very well in buildings that have consistent heating loads and cooling loads throughout. So let's take a look. How do they work? And how does an air handling unit work in general? Well, we draw air in through the return section of the air handling unit. And if it's design day cooling mode, we'll draw in a minimum amount of outdoor air for minimum ventilation. As that air moves through the air handling unit, a lot of things are happening to it. But in this case, most importantly, that air is being cooled before it is then delivered to our spaces to reject the heat out of the space. Okay. And that air that we return will make its way back to our air handling unit's return section, as we can see here. Okay. Pretty straightforward. So once we get back to the air handling unit, a large amount of that air will be recycled and sent through the mixed air damper to mix up with our minimum outdoor air, and a small amount will be exhausted outside. Okay, so let's go a little bit deeper. In a constant volume system, the supply air temperature is varied while the volume delivered is constant. Okay. So before I move to single zone disadvantage, how do we determine the CFM requirements of an air handling unit? Well, that's an output of the engineer's load calcs. How do they do a load calc? Well, the engineer will take into account the heat generation that they see in these spaces during summertime operations. So that might include solar gains, it might include plug loads, lighting loads, and people. And they'll take into account the size of the room and the envelope of the building. What are the R factors and losses we're going to see through the exterior walls and so on. So one thing you might experience in a single zone constant volume system is the single zone disadvantage. If I have the thermostat in this system tied to a large conference room where we have a lot of people inside, there's lights on, and we've got a large solar gain, I'm going to need to provide some cooling to that space. What invariably will happen to the other spaces? They'll be overcooled. Okay, so constant volume systems are not great when we have variable loads in the building, when we don't have that nice constant cooling or heating load. So generally, they can be inefficient, but they are low cost and simple to install. Okay.
Yeah, and I know for folks been around a while, this is obviously we've experienced this. We're pretty familiar with this, but if you're new, this is like a big deal.
Sure.
Right? And
Sure.
I've been on a lot of jobs that, jobs that are budget sensitive might get designed around VAV, and then after the fact, you're called to a job site meeting, your unit's not controlling the temperature, and you're like, okay, where's the thermostat? And you go look at the thermostat and you say, well, you're asking it to be 72 and it's 72, but it's cold in so and so's office. Well, that's the nature of this type of system. So it's kind of important if you're new to grasp that. Us folks have been around a while. We know we've experienced all that, but just wanted to
Sure.
throw in
No,
my 2 cents on that. So
excellent point. Yeah, it's the VAV, as we'll see, produces that multi-zone control, which everybody in an office space loves. Everybody gets their own
mhm.
temperature. So possible solutions to these temp control issues we see in constant volume systems. Well, before VAV, what did we have the options to do? We had the options to provide more air handling units, right? I could put 2 small fan coils inside those smaller offices to help alleviate these overcooling issues. You might see terminal reheat thrown on these in the field if it's a constant volume system, or cooling and heating at the same time. Not really allowed to do, but you'll still see it. And before VAV, we saw in the industry a lot of dual duct systems. So what's a dual duct system? Well, it's an array of 3 sets of ductwork, one of which is a return section, and the other 2 are supply. Those 2 supplies have a hot and a cold side. So I might have a hot air duct delivery system and a cooled air delivery system, and I'm mixing at the terminal, which each have their own thermostats tied to them. Okay, so we'll still see these. Tony, do you see these where you're at? We see them up in Ohio quite often, remnants of the past that we sometimes are replacing the air handling units on.
Yeah, is that similar to a multi-zone system?
Yep. Correct. Yeah.
We
Whereas a
see,
multi-zone, I always like to say, imagine all of the dampers that you see in my little graphic here
mhm.
shoved back into the supply section of the air handling unit.
Oh, this
Right.
is a dual zone system.
Yeah. This is a dual duct here and a
I have not.
multi-zone.
A dual duct. Sorry. So I don't think I've seen a lot of those in the
Yep.
southeast. I've seen a lot of multi zones.
Sure.
Mostly
Yeah.
they're being replaced. They're great in terms of temperature and humidity control. I just don't think they're not as efficient as
Absolutely.
newer systems. But do you
You
see a
got
lot
it.
of these types of systems where you're at? Older systems?
We do. Yeah, we do. We just had a multi-zone job in Canton, Ohio that we were designing, and yeah, a lot of replacement work
Mhm.
will replace multi-zones or dual duct air handlers. So, but the better solution is the VAV option. So, what is VAV, variable air volume?
Mhm.
Well, it's a system in which the supply air temperature is constant And we'll see as we move forward that temperature rule of thumb for the industry, if you're new, 55 degrees out of a VAV system is a pretty good rule of thumb to use, whether that's summertime or winter operation. Okay. The supply air volume is obviously varied, and it allows spaces to operate as independent zones with one set of supply ductwork. And we achieve very efficient operation out of these systems. So what's it look like? Same type of system, except now we have VAV boxes, as you can see, at the terminals of each of our spaces, which are now separately zoned, and they each have their own thermostat. So the trick is inside of this VAV box, we have a reheat coil. Okay. So as we deliver 55-degree air out of the supply section of the air handling unit, and a space on the left of the screen that we see here that might be getting overcooled, we will be able to rectify that issue by providing some heat and delivering nice, warmer or room neutral air to that space that's being overcooled. Okay, so independent temperature control for each zone. Okay, each VAV box is capable of measuring airflow, which allows us to ensure minimum ventilation is being achieved at each of our zones. And most importantly, for a VAV system, we're applying variable speed drives to the supply fans and to the return and exhaust fans if we have them. How does that VFD know what to do? How does it know to tell the fan to speed up or speed down? Well, we place a duct pressure sensor in the supply ductwork. We set a control head, as I like to call it, coming from the pumping side of the industry, to let us know if we're meeting the static requirement or if we need to turn down. Why would we need to turn down? If the dampers on the VAV boxes have all moved towards minimum position and we're building up pressure in the ductwork, we're going to slow that fan speed down. Okay.
Nice.
Okay, so let's get to the fun part of this presentation. Here's what I love to talk about.
Hey Mike, could you go back to the previous slide? We had a question about terminal reheat.
Sure.
Are you going to talk about that later, or can we bring that up now?
Oh, no, we can talk about it now. Absolutely. Go ahead, Tony.
So when we're providing 55-degree air to the space, the other huge benefit to this is, you're always dehumidifying the air, right? You have the coil. So in a constant volume system, if you're not changing the CFM, the only thing you could really change is the supplier temperature, unless you're reheating. That's a whole other discussion, which we do a lot of reheat with package DX systems, and that free reheat, it's energy we would normally be throwing out into the atmosphere. So, but in a constant volume system, like a chill water fan coil, classic, or, 10-ton, 5-ton unit serving a space, constant volume blower coil, the only option, if it's getting too cold, is to elevate the temperature. And is that a problem? In most cases, probably not. But if you're in the Southeast and it's a cool, rainy day, like today, if it's 68 degrees or 70 degrees and it's rainy and you start elevating that temperature, you're going to have some pretty serious humidity issues. So therein lies one of the major problems with, single zone constant volume and even multi-zone. So what the benefits of the VAV system is, you're always locking in at that 55 or even 52-degree air, depending on where you're at.
Sure. No, that's a really good point. And I think to add to that, Tony, one thing I see with the VAV boxes with the reheat coils in today's world, people like to run, the specifying engineer likes to run really low boiler water temperature to that hydronic coil in the VAV box. And I guess a good rule of thumb, if you're running that low temp, make sure you're specifying a 2 or 3 row VAV reheat coil. When you're running 180 and 160 return on that boiler water, sure, one row coil will cut it. But as we get lower on that boiler supply temperature, we have to get more surface area on that coil to transfer the heat.
That's such a good point. I actually had a job where it was specified 180 for the water, and it was specified 1 row coils, but they changed it to 140 and it didn't get caught in time. So all the boxes we shipped had one row. So it was, I think they had to be all retrofitted because that won't do it at 140. But so what's your experience with as far as terminal reheat? So we're leaving at 52 degrees in a VEV systems. At some point, it's overcooling the space at part load because it's designed for full load. We're bringing that, we're slowing the fan down. So we're lowering the CF end of the space, but still at 52 degrees. At some point, you're at a minimum. You can't lower the fan speed anymore. The dampers may be locked in at 30% or whatever. So what do you, in terms of reheat, it's okay to use boiler water for reheat, electric heat. I mean, I never had a problem with specifying that, but.
Sure. Sure. Yeah. I mean, in Ohio, we will see hydronic reheat quite often. Gas is very cheap here, so we're typically seeing that that reheat water supplied through a gas-fired boiler.
Right.
But yeah, you're correct, and I think that's one important note as well. You know, if we want to dehumidify, maybe we're dropping down to 52, 53 degrees off of the coil, catching some reheat on the fan motors, and then obviously, like you're saying, reheating at our boxes to maybe 95 degrees to then provide the heat to the space.
Yeah, that's great. We did have a question here from Jonathan Suture. Let's see here. Location of the duct static pressure sensor. That's a common question.
It is. Now I'll answer from the hydronic side, and I'll throw to you, Tony. So on the hydronic side, you'll hear, "Hey, throw that out at the furthest run, maybe 2/3 of the way out into the system." For the air side, Tony, do you want to take that one?
We usually hear 2/3 down the duct. You know, there are other strategies, like one of my favorite strategies, and it's been a while, so I'm probably going to butcher this, but I think it's called static pressure reset, which is you basically look at the position of the boxes and you want them all to be as open as possible because it's less pressure. So you reset the static pressure so that they're all, or the worst case one is 90% open or something like that. So if you put it 2/3 the way down the duct and say 2 inches all the time, you might not need 2 inches because at part load, all the boxes might be shut. So,
Right.
anyway, so.
Now, great points. Okay. So let's get into the air handling unit itself.
Can I
What's
make a quick announcement here? If you're, well, I was going to announce for people who can't hear us, but they're not going to be able to hear this. But there is a mute button on if you hover over the live stream on the website, there's a mute button there. I think by default it's muted. So you got to go there and unmute it. And I think, Courtney, why don't you try to drop that in the chat? Because if they're muted, they're not going to be able to hear me. But I'll have to hold up a sign or something.
Perfect.
That's a good reminder, though. Sorry, Mike, go for it.
No, that's fine, Tony. Yeah, absolutely fine. So let's talk about the air handling unit itself. What's it made of? Okay, there's a number of components. When we're selecting these components at Northrich, at the air companies, you know, what are we choosing from? What can we offer the engineer? Well, first and foremost, we have economizer choices. Okay, and then we'll have some fun with my cartoon depictions of these components, but we might see a pre-filter. Maybe there's a preheat position heating coil. Maybe we have some humidification as depicted by my watering cans there. Okay. We might have a chilled water coil. Maybe there's UV lights for sterilization on that coil or providing decontamination to the airstream itself. Okay. We might have a reheat coil, a reheat position. Maybe, well, we'll definitely have a supply fan and maybe a final filter. Okay. Now let's have some fun and let's talk about what I think is one of the most important components of an air handling unit. And that is the box itself. Okay. So the box, what are we talking about when we're talking about the box size of the air handling unit? We'll hear that term a lot out in the field. What box size are we looking at here? Well, we're talking about the length and the width and the height of the air handling unit box. Okay, the cross-sectional aspect ratio of the box. How are we determining the size that box needs to be? Okay. Obviously, as we go up in CFM, we're going to see a larger air handling unit. As we go down in CFM, we're going to see a smaller air handling unit. But let's get into the nitty gritty of what the width and the height is a function of. Okay. It's a function of the design CFM that the specifying engineer has called out, and potentially the cooling coil, potentially the heating coil, and potentially the air filters. That's a lot of potentials. So let's talk about what I mean. Okay. And to do that, let's remember a certain equation from fluid mechanics back in school. This Q is not heat transfer. This Q that we're using here, I like to make it as confusing as possible, Tony. This Q is volumetric flow rate. Okay. CFM. Our CFM is equal to the face velocity times the cross sectional area. Okay, Q equals VA. So if I want to determine the height and the width of this box, I have to limit one of those variables, either face velocity or cross sectional area, right? Because we're assuming the engineer has called out the CFM. How do I apply these limits? How can I apply a velocity limit if I want to output the area? Well, if I'm working in an air handling unit that has a cooling coil, I might limit that face velocity to around 500 feet per minute, which is a good rule of thumb for new engineers entering into the HVAC space. Why 500 feet per minute? Well, that is the velocity at which we're typically not going to dislodge condensate droplets off of our cooling coil and send them down the rest of the air handling unit to corrode the duct work or damage our filters and fans, right? We want to pull moisture out of the air, turn it into liquid water, and let it drip down the cooling coil and into the drain pan of the chilled water coil. We don't want to dislodge it. So if we keep that velocity at 500 feet per minute, we avoid condensate carryover. So maybe we're limited by the cooling coil. If we have a unit that doesn't have a cooling coil in it, maybe there's just a heating coil inside, we might limit that velocity to 700 feet per minute. Some people might say a little bit higher. So in this case, we're not concerned any longer about dislodging liquid water. We're only providing sensible energy. There's no condensate concern when we're heating. We're more concerned about noise generation and excessive pressure drop over the heating coil. So 700 feet per minute is a good rule of thumb if we're talking solely about a heating coil. And air filters also have to be taken into account. So if I look at a MERV 13 4-inch pleated air filter, I'm going to see a maximum air velocity that the manufacturer states we're allowed to press over that media. And if we don't follow that specification, we might collapse the air filter or at least reduce its effectiveness.
That's good stuff. We did get a comment.
Sure.
We should not do that anymore. Need low pressure drop design. Well, yeah, but we don't make that decision typically. What usually happens is we send our ideal selection to an engineer and he sends it on and the architect's like, we don't have that much room. You got to make it smaller. And it gets shrunk down based on those parameters, not on the science behind it, because obviously the lower the pressure drop, the lower the energy consumption, the lower the acoustics. There's so many benefits to it. You get more room for maintenance, but unfortunately we're not the sole, decider on that problem. And depending on what the, depending on what the job site budget is, it all goes into that. So I agree. It all should be 350 to 450, but it's not in the real world. It doesn't seem to happen that way. So.
Sure. Yeah. And just another point for our more experienced engineering audience, that 500 is a good rule of thumb, but the decision at which velocity is acceptable over a cooling coil to avoid condensate carryover is a function of fin density as well as fin material. So as I tighten up in my fin density, maybe from 8 fins per inch to 14 fins per inch, my velocity allowance goes down. Now, if I'm more on the 8, 10 fins per inch, I might be able to push that 500 a little bit. Good point. It is a case by case basis that we could get into, but for a rule of thumb, 500 is a good, hey, I'm out in the field and I need to determine how many CFM this air handler has rolling through it. So let's take a look at that type of example. If I have a 20,000 CFM air handling unit and I hold that velocity to 500 feet per minute, maybe there's a cooling coil inside, I'm able to output that coil face area. Okay, and I can use these equations in reverse as well. If you're out in the field and we see a coil face area of 40 square feet, and we know that there's probably a 500 feet per minute velocity limitation, I can understand how large my cooling coil is. And a quick rule of thumb, if you take that cooling coil surface area, multiply it by 1.3, now we're talking about the total cross-sectional area of the box, the actual box size. So if I were to output 50 square feet, when I multiply it by 1.3, I could understand that maybe we have a 5x10 or a 7x7 box size. Okay, that would be acceptable.
Yeah. Mark Kipp said, an architect didn't allow enough room. I'm shocked.
Every day of my life.
Hey, we love the architects, man. They're trying to do their job too. We get it. We get it. And that's, it's all about the dollars. You got
everybody's
people
vying for space.
Yeah, it's about ROI and usable space. And
you got it.
And not everybody thinks that a custom air handler is beautiful like we do. And they're like, why would you want that? This is just such an amazing piece of machinery here.
That's right. And I would encourage everybody who's getting pressed for space in that mechanical room to investigate that fin density and maybe even consider split coils if you can grow in length on the air handling unit and maybe not in width. And you expand that face area with split coils or staggered coils and allow yourself a smaller box size.
Sounds good.
Perfect. Okay, so construction materials. What do you typically see? Well, material-wise, we can construct these air handling units out of stainless steel, aluminum, or galvanized. Typical construction is going to be double-walled, where we have an interior skin and an exterior skin divided by injected foam. Okay, it's 9 times out of 10 for me, Tony. It's injected foam in today's world. I know there used to be more of a fiberglass fill type of construction for these air handling units. I believe fiberglass fill does a little bit better on sound reduction, but 9 times out of 10, standard construction is going to be double wall foam injected. And we'll have options for 2-inch, 3-inch, or 4-inch. Now, those R values I'm showing, the resistance to heat transfer that each of those wall sizes are capable of producing, those can be variable from manufacturer to manufacturer. I know there's been some upgrades in those R factors as time's gone on over the past 5 years or so.
Do you see a lot of fiber anymore? I think you mentioned.
Yeah, in the
10% of the time.
Past 3 years, I've seen maybe 1 or 2.
We don't see it much anymore.
Yeah, it's you wind up having to increase the wall thicknesses, the actual metal, because you lose the structural integrity that the injected foam provides for the unit when you go to the fiber fill. So it could be a more expensive unit when you go to fiber fill.
It's funny. I was thinking when I started, single wall was the standard fiberglass, foil faced fiberglass.
Wow.
And double wall was an upgrade. And when we started double wall and everything, that's when the condensation problems happened on the exterior. Like a single wall unit with fiber insulation didn't sweat very much.
Yeah.
We started double walling it. Anyway, but yeah, we typically see the foam. The foam is a better R value and it's extremely strong. Like if you've ever gone up to a foam panel and given it a good whack, it's like a rock. It's really solid. So
you got it. That's right. So I think a lot of engineers will look at this L over 240 up to plus minus 12 inches of water column. What's that mean? Well, that's a deflection call out. That means that the manufacturer is guaranteeing that at plus 12 inches of pressure inside the air handling unit or minus 12 inches of pressure, that the unit will not deflect more than 1 inch over a 240-inch length. So if I were to put an indicator on the outside of the air handling unit wall and I pressurized it, we're not going to move that indicator greater than 1 inch. It's a deflection call out. Okay. And lastly, base rail. What are we building this unit on top of? We're using base rails for structural purposes, but also for the ability to trap and drain down our cooling coil drain pan. Okay. And you'll see those options in structural steel or aluminum typically. Okay. Moving forward, let's talk about the best part of this presentation, which is the economizer.
And before you go on to that, the base
Yeah.
rail, the higher the static pressure of the unit, the more room you need for a trap. And if you've ever gone to a job site and seen a hole cut in the floor, it's because they
Yep.
didn't have enough room for the trap. And it's a very unforgiving situation when you have a 40,000 CFM air handling unit sitting on a slab in a room and it's not, you need another inch. You just gotta,
Yep.
It's not easy to raise it up an inch. Let's just say that once it's installed.
Somebody winds up hitting concrete with a sledgehammer. You're right. You're right, Tony. So the economizer, what are we doing here? What's the economizer? Well, we're doing two things. We're achieving the ASHRAE standard 62 ventilation requirements, and we are providing free cooling to our spaces through the use of the economizer. So I always point out on this slide, a lot of time was spent on it. If it's a hot summer day, indicated by the red arrow on the outside air damper up here, and we're trying to cool in a VAV system to 55 degrees, we might be returning 75, 63 or so to our return air. The economizer gives us the ability to provide free cooling. Okay. If it turns out it's 54, 55 degrees outside, instead of using mechanical energy to cool the incoming air from the return mixed with a minimum amount of OA, I might fully open up the outside air damper, not provide any mechanical cooling, simply move through my filtration and gain pressurization with my supply fan and provide it to the space. I would then return at 75, 63 and send that return air directly outside through the exhaust air damper with the exhaust fan in this case. So in this case, again, I'm not having to provide mechanical cooling. Okay.
Do you have a lot of days in Ohio that's applicable?
I feel like it's less and less, Tony. It seems like we're either in a hot summer design day all summer, or we are having a pretty cold winter. I will
Crazy
say
cold. Yeah.
this winter in Ohio started off, or I should say fall. It's been pretty temperate. So I think there's been some shoulder months here where there's been some energy savings for building owners in Ohio. But to that point, when we can't utilize free cooling and open up the OA damper, we're keeping it at a minimum position to allow for the minimum ventilation requirement to bring oxygen into the space and expel VOCs and CO2.
Nice.
Okay. All right. So what options do we have when it comes to economizer options? When we're selecting these, or the engineer has specified this is what they want, this is what we have the options for. Barometric relief to start off. What's that look like? Well, I've done this in more of a diagrammatical fashion here, but we can see the air handling unit, the supply section where I just have a little filter and a heating coil and a fan, and our conditioned space, and then our return section. We divide those two by the mixed air damper or the return air damper, whatever you want to call it. And what can we say? Well, the barometric relief damper style economizer uses a barometric relief damper, which we can see highlighted in green on the upper left side. Okay. This damper is going to open. It's a weighted damper. It's going to open at a set pressure to relieve the building of overpressurization. The important note about barometric relief, barometric style economizers is this supply fan has to be sized to cover the pressure drop of both the supply ductwork as well as the return ductwork. Okay. So thinking a little bit ahead here, do I want to use that supply fan when I have a lot of return pathway ductwork? We'll talk about that. The answer is no. Okay. Moving on to exhaust fan style economizer, you can see I've added a fan to the left of the return damper. Okay. I still have my supply fan. What's going on here? Well, instead of just relying on a weighted damper to expel our air, now we've got some static capability with an exhaust fan. In this case, the important takeaway for specifying engineers to understand that our supply fan still has to be sized for the supply ductwork drop and the return ductwork drop. We'll size the exhaust fan for our exhaust and the return ductwork drop. So we have a little bit of an overlap there, which allows us to move into economizer mode and let the exhaust fan maintain or cover the drop of the return ductwork. But most importantly, it lets us maintain space pressurization. So how is that exhaust fan controlled? Typically a space pressure sensor in the conditioned space. If we're trying to maintain plus 0.1 and we are over pressurized in the space, our exhaust fan will modulate on and relieve pressure out of the building. Okay.
I always think of it as the supply fan gets it to the exhaust fan.
There you go.
That's kind of like how my brain works. But
Sure. Yep. That's right. And we'll get a little bit more into control, but I always say that's the big takeaway. If we're controlling an exhaust fan, we're controlling it by that space pressure. There's a lot of energy advantages to using exhaust fans. They're not always on, right? We might have exhaust fan in the off position while the supply fan is covering the supply ductwork drop and the return while maintaining adequate space pressure. Okay. Lastly, sorry, I skipped ahead there. Lastly, we have a return fan economizer option. Looks a lot like the exhaust fan economizer, except now you can see the change in position of the return fan. Okay. In this case, I'm covering the supply ductwork with the supply fan, its drop, but I am not covering the return pathway with the supply fan. In this case, I'm covering that with the return fan. The return fan is on at all times. That's how this differs from an exhaust fan economizer. The return fan and the supply fan are on at all times. Typically, we'll see a control scheme in which the return fan is tracking the speed of the supply fan. Can make things a little more difficult with the varying airflows we see in the conditioned space in a VAV system, but doable. Okay.
Great if you have a, rooftop unit on a 3-story building and it's providing all 3 stories. If you have a long, I guess, return duct or high pressure drop return duct, those are great too.
You got it. I always seem to land on return fans in hospitals. They seem to have return pathways that are, 2 inches, 2.5 inches of drop.
Yeah.
So,
This is great. That's a great rundown because there's a lot of confusion in the industry about that. It took me a long time because we didn't do a lot of economizers being in the Southeast, and I would have to go in and look at the difference between return fan economizers, exhaust fan economizers. It's good stuff.
You got it. Okay. So how do I decide between these if I'm the specifying engineer? What are the decision drivers? Really, they're pressurization. Okay. Pressurization can affect a number of things: comfort, performance, security. American with Disabilities Act, we can affect a number of things: system type, installation cost, operational cost, and efficiency. Okay. All of those are decision drivers, but pressurization being, in my opinion, the most important. Most of the time in a conditioned space, if we were to say a rule of thumb, we'd want to maintain slightly positive pressure in the space, maybe plus 0.1. It's not always the case. If we were in an auditorium, a pool room, for example, we might want to maintain a negative space pressure to disallow that chlorine-filled air to escape to our other spaces and corrode equipment. But typically, plus 0.1 in a commercial comfort cooling application is typical. Okay. So let's ask some questions here. Is barometric relief economizer a good choice when the return pathway has a medium or large pressure drop? I'm using generalized terms here, medium and large. And the answer here is no. It's no. When that return pathway pressure drop is large, we end up having to overpressurize our space so that we have enough, pressure to make our way back to the barometric relief damper and the suction side of our fan. So we only want to use a barometric relief economizer when we have little to no return pathway pressure drop. What about when the building's tall? The building is tall. Should I use barometric relief? The answer is no. And the reason is because of the stack effect. Hot air likes to rise. That can build a pressure in ductwork, sometimes a pressure that's great enough to crack open a barometric relief damper and exhaust air when we don't want air exhausted. Okay. What else? An exhaust fan economizer. Is it a good choice when the return pathway has a large pressure drop? Well, this is a good slide. I'll say it's one of the best if you're an experienced engineer on this call. Okay, when there's a large return pathway drop, should I use an exhaust fan economizer? And the answer is no. And here's why. You can see on the top of the screen, when I have that excessive return drop, I'm pulling a pretty large negative on that exhaust fan. Due to its position, what can we see typically happen? A short circuit of our outside air through the mixed air damper right back outside. So you think
That's a great slide.
yeah, it's
I never really thought of that.
this is a Johnson Controls adapted slide here, and
Gotcha.
they do a good job of explaining that short circuit
Mhm.
can come back to bite you. You think you're providing that minimum OA, and you're just circulating from your outside to your outside. So on the bottom
point.
part of the slide, we can see a more appropriately sized return fan pressure and return ductwork pressure drop. Here, we can see how flow is induced to the supply fan suction from our outside air position, as opposed to short circuiting due to that negative pressure on the exhaust fan. Okay.
Very good.
Yes. There we go. Okay. What about when the system is a VAV design? Well, that's a great option for an exhaust fan economizer. Again, we're controlling that exhaust fan based on space pressurization. So the varying airflows that we'll see out of VAV boxes tie up well with an exhaust fan economizer. Okay, and another generalized term here, small or medium pressure drop, sure, right? We don't want to overextend ourselves on a high pressure drop with an exhaust fan economizer. What about return fan? Is it a good choice when we have a return pathway with a large drop? Yes, we covered that. Tony, you talked about it. Okay, we're not going to
I
see that
stole your
short
answer.
circuiting
I
issue.
stole your thunder.
Yep.
Sorry about that.
It's okay. We're not going to see that short circuiting issue. Is it a good option in VAV design? It can be. We do it all the time. It's a little bit more complex on the controls. As I said, typically a supply fan is going to be controlled via the feedback from our duct pressure sensor, and the return fan will track that speed. But typically, we'll see a dual input controller to maintain space pressurization requirements. So, if I were to summarize this with a nice chart from one of our manufacturers, what would we see? Well, looking at the far right column, this is how you should be deciding between these options. If you are 0.1 inches of water column or less on your return pathway, use a barometric relief damper. Okay. If you're between 0.1 and 1, use exhaust fan. And if you're greater than 1, use a return fan economizer. And we can see some other notes here about advantages and disadvantages. I won't read them all, but there are some important ones. Obviously, the lowest first cost is going to be electric relief. It's not a fan that we're having to supply with that economizer, just our supply fan in our unit. Okay, but you got to be careful of that overpressurization issue you might find in the barometric relief. The exhaust fan's a lower first cost than the return fan. It's suited well for VAV design. And the return fan is the highest first cost, but is able to cover the larger return pathway drops. So good resource here for a rule of thumb chart. I'm sure we'll share this with anybody who's interested. Okay, so let's have some fun. Trivia. What is this? This is a sling psychrometer. And I like to throw in here, what speed do we have to spin this sling psychrometer at in order to get an accurate wet bulb reading? Meaning there's a saturated wet piece of cotton on the end of the thermometer, creating an evaporative cooling effect. And if we spin that at 900 feet per minute, we're going to get a good wet bulb reading. Why do I
There we
bring
go.
this up? Yeah, there you
Mike,
go.
you missed it. I got one right here. I don't have a lot of chances to use my sling psychrometer. What better chance to use it on? Right. What better chance to use it on what my wife calls the all-day nerd fest, which is what we're doing right now. So there you go.
There you go. So why do I bring it up? Well, economizer control. We see these options: dry bulb control, single enthalpy, dual enthalpy, whether we're laying out a rooftop unit, an air handling unit. What do they mean? Well, if we're talking about dry bulb control, it means I have a dry bulb temperature sensor in the outdoor environment, and I have a temperature at which I will decide to move into economizer mode or free cooling mode if I meet that temperature or am lower than that temperature. So, in other words, if we're using 55 degrees as our tipping point, if the ambient air outside is greater than 55 degrees, we will maintain minimum position in the outdoor air damper and simply just bring in enough ventilation to meet our requirements. If it's lower than 55 degrees outside, and that's our tipping point for our dry bulb control, we will close our return air damper, our mixed air damper, and we will open up our outside air and our exhaust air and flow fully through the air handling unit with outdoor air to provide that cooling and shut off mechanical cooling. That's how we use dry bulb control. Now, many engineers might say, I don't want to bring in all of the humidity that might exist on a 55-degree day when it's raining outside. Okay, what do we think about that? Is that a good answer? Is dry bulb going to be accurate enough for us if there's these days when the latent energy of that air is very high, maybe near saturation? Well, the psychrometric characteristics of the air we're typically cooling off of our cooling coil in a VAV system, whether it's DX or chilled water, are 55-55. Okay, so fully saturated 55-degree air, which is the temperature of the wet bulb when it's raining outside. So what do you think, Tony? Can we let in that 55-degree air on a rainy day?
I would.
I would too. There's probably some considerations regarding not getting velocities and not bringing droplets inside, but theoretically we should be able to bring it in.
I just look at it on the psych chart, but you're right. If it's storming real bad and you could actually pull in water, that's different. But
right,
yeah,
you got it. Okay, so single enthalpy and dual enthalpy. What are they and why use them? These are scenarios in which we either have two enthalpy sensors, dual enthalpy, one in the return pathway ductwork and one in the outdoor air, or we simply have a enthalpy sensor in the outdoor air environment and a canned data in the controller to compare to. But why are we potentially using enthalpy control? Because we're leaving money on the table when we compare it to dry bulb control. Okay. And that is best explained through showing an example of what's called integrated enthalpy control, where we're potentially deciding to cool outdoor air as opposed to cooling our return air mixed with minimum OA. So, for instance, if I'm at 10,000 CFM and I'm bringing back return air and mixing it up with some outdoor air, producing a mixed air condition of 80-67. And I'm trying to cool to 55-55. The BTUs required to meet that cooling load are 348,000 BTUs. If I'm 55 degrees outside, fully saturated, 55-55, and I'm wanting to deliver 55-55 to the space, no mechanical cooling is required, 0 BTUs. But what about 63-59? If I want to move 63-59 to 55-55, I'll require 114,000 BTUs. In this case, if I had integrated enthalpy control on the air handling unit, it would be better off to cool the outdoor air than to cool down the return air mixed with minimum OA. And lastly, 7368. How much does that take to get to 5555? 386,000 BTUs. In that case, I am better off cooling the mixed return air on the far left in red and providing less energy to mechanically cool that air. Okay.
That's great.
In single enthalpy control, I'm comparing the outdoor air enthalpy with CAN data within a controller inside. You'll see a controls contractor choosing one of those A, B, C, or D curves for the comparative information and the choice to move to economizer mode. Okay. All right, great. So we're moving towards the end here. I'm going to move pretty fast because I know we're coming up on time. So what else do we see in the air handling unit? And these will just be very high level summaries of these components. Well, we see filters. Okay. And the takeaway for a new engineer in the space is filters need to have controlled pressure drops and phase velocities, just like coils. So a lot of times, instead of a flat filter, we'll see what we see here on the bottom right, an angle filter, where we're increasing the surface area, the face area that the filtration media is seeing, essentially dropping the face velocities and increasing the effectiveness of the filtration. Okay. And we'll have a bunch of options here. Typically in my world, I'm seeing a MERV 8 pre-filter and a MERV 13 or MERV 14 final filter. If it's a hospital application, we're more up in that MERV 17 through 20 HEPA level filtration. Okay. Okay, we might have preheat, chilled water, and reheat coils in the air handling unit. And why might we have that, especially in a single zone unit, that reheat in a single zone unit? Well, if we look in the bottom left, we can see a little diagram of what a dehumidification process looks like. Our mixed air condition comes in, hits our chilled water coil. We cool down to 52 degrees at 95% RH, wringing out that moisture from the air into condensation in a drain pan. And then we'll use that reheat coil to reheat the air we deliver to our space for comfort and to avoid condensing on surfaces with too cool of air. Now, in an energy efficient world, we're doing that with either a wraparound coil or we're doing it at the VAV box when we're reheating. Okay. And towards the end here, we might see humidification in the air handling unit. Isothermal and adiabatic are really the two options we have when it comes to the technology style of the humidification equipment. Adiabatic being when we utilize the energy from the air to evaporate atomized liquid water. Okay. We're taking liquid water, putting it through a nozzle, spraying it into the air, and using the heat energy from the air to turn it into gaseous water. It's a very efficient way of humidifying, very, very inexpensive operational cost, typically more expensive first costs. In isothermal humidification, it's the one we all think of, a bucket of water with a heat source beneath it, and we're boiling that water and providing that humidification and phase change with heat energy we're adding to the liquid. It's going to be a little less efficient, and we're going to add a small amount of heat to the air. Most of the energy is put into the phase change of the liquid to the gaseous water, but you'll have some amount of heating due to the heat coming off of the dispersion tubes in the ductwork. Okay. We might see UV sterilization on the face of the cooling coil to avoid mold and mildew growth. We might even see it in the airstream to contaminate as we pass the air through the air handling unit. One big thing about UV sterilization, no matter who you go with, you're reducing maintenance requirements with cleaning coils, and you're actually maintaining a better amount of heat transfer. We can see here just with a 0.02 of an inch of biofilm buildup on a cooling coil, we reduce the heat transfer significantly. The most important piece of this for everybody on this call, though, is never enter an air handling unit when these lights are on. There should be a kill switch when you enter an air handling unit that kills these lights, but these are UV-C, I believe, and those will burn your eyes and give you a tan you didn't want.
Mm-hmm.
Okay, we've got fan options. In yesterday's world, we had a lot of centrifugal fans that were belt driven, 1 or 2 per air handler. And in today's world, we have an array of fans, typically like we see on the bottom right, where we're reducing the density of that horsepower, spreading it out over a number of fans, and create a serviceable and easy, redundant fan system. Okay. We're towards the end here, guys. So I'll lastly talk about heat recovery, something I see in every school job that I do. So heat recovery is when we're taking that enthalpy from our return air, or in cooling mode, we're taking the sparsity of the enthalpy from the return air, and we're using it to our advantage. Before we send it out to the outdoor environment to meet our minimum ventilation loads, we're grabbing the heat energy off of that air, transferring it by the rotation of this heat wheel to the air intake side, and eventually the supply air to our space. Okay. So for sensible and latent energy recovery, we can use energy recovery wheels, and we can use plate heat exchangers. We have enthalpic plate heat exchangers that will do both ends of the energy, both latent and sensible. Most of the time, most people probably see plate heat exchangers as a sensible only type of energy recovery. The important notes about these recovery options are contamination. With energy recovery wheels, I'm going to see some cross-contamination of the exhaust airstream with the supply airstream, which may or may not be a concern for you dependent upon your application. That cross-contamination drops significantly when I move to a plate heat exchanger and goes to 0 when I'm using a runaround coil. The only catch, the runaround coil is the least effective. Payback takes a number of years. Okay, well, that's the end of the presentation, and I'll go ahead and do some questions here, Tony, if I'm doing okay on time. I know I'm a little bit over here.
Yep, go for it. And then after this is still the PDH
Yep.
portion questions, and these questions are required for some of the states just to ask questions. You don't have to have a record of them. After this, we're going to take a quick intermission. Then we're going to do the giveaway questions, which is a separate set of questions. So just not to confuse everybody, but go for it. You can go through these. Yep.
That sounds great. So which material is not typically used for air handling unit walls? Stainless steel, aluminum, galvanized steel, or copper? Let everybody take that one in.
I think I could guess that one.
Tony, you want to take a swing at it?
I would say copper.
That's correct.
I've never seen a copper cased unit, but I have. Hey, Heather got it right. Good job, Heather. But I have seen copper coils, but thin coils.
There you go. That's the right answer. Okay. What's the maximum deflection limit for air handling units? L over 100, L over 200, L over 240, or L over 300? How much can I allow that air handling unit to deflect? Okay, and the answer here is L over 240. Again, I don't, that standard will only allow the air handling unit when pressurized to deflect 1 inch over a 240-inch length.
We got tons of answers in the chat, by the way.
Good.
All correct, too. So people are paying attention. That's good.
I'm glad to hear that. What style of economizer has the lowest first cost? A return fan economizer, an exhaust fan, barometric relief, or no economizer at all?
That's so easy. It might be tricky. It might be one of those trick ones.
That's
No, I'm
true.
just kidding.
So, although no economizer would be our cheapest option, that is no economizer. So,
I was wondering if that was kind of like a tricky deal, but
if we're looking for an economizer that's of lowest first cost, barometric relief is going to be the option there. Okay. Which style is best suited for systems with high return air static pressure? Which economizer style for high return air static pressure? Barometric relief, exhaust fan, return fan, or economizer free cooling?
boy, we're getting a ton of answers. This is great. A lot of engagement in the chat, by the way.
Good.
Mike can't see the chat. That's why I'm telling him.
Glad to hear it. All right, our answer here is going to be that return fan. Whenever we have that drop over 1 inch of return pathway pressure drop, look at that return fan economizer as your number one choice. Okay.
Nice.
And I think lastly, what is the recommended limit for return air? I usurped myself, Tony, for return air pressure drop for barometric relief systems. Maybe I didn't. Recommended limit on return air pressure drop for barometric relief systems. Where do we limit that barometric relief economizer to? That answer, to avoid overpressurization of our space, is going to be B, 0.1 inches of water column.
Nice.
Good job, everybody.
Awesome.
Okay, that'll conclude.
Well, you did a fantastic job. I love the basics, you know, Air Handlers 101. And even though I've been around for 25 years, I'm like, I never really thought of that. Or, oh, yeah, I forgot about that. So I got to hear them too. So
good.
Super great presentation. We appreciate it. So if you're watching, hang out. We're going to do a quick intermission. Then we're going to do a giveaway. And then our next presentation starts at 10:30. Okay, so we've got a little bit less than an hour here. Mike, you did a fantastic job. If you need your PDH certificate for this class, just scroll down below on the website. You could download. There's one special one for New York, and then there's one for the rest of the states that are shown there. Again, if you're watching this right now on LinkedIn, please come over to the website. This is where you can get all the full experience of the PDH credits, and you could ask questions and stuff like that. We're streaming on LinkedIn too, just to bring people to the website. If you're rewatching this on the YouTube channel or podcast, look in the show notes or the video description, and you could just email me, and I'll send you the certificate if you want to rewatch it. And don't forget to share this right now. If you want to copy the URL of the website, share it with your coworkers, share it on social media, get more people to the site. We greatly appreciate it. I think we've had close to 450, 500-ish people watching. So that's just great. And that doesn't include the LinkedIn folks, which is probably double that. So